Alright, so let's look at this problem and see if we can make sense of it now. So there's the picture of a ball falling, and if I dropped it, it wouldn't look like that, right? Because I'm not throwing it. I'm not exerting any horizontal force on it. I drop it, it looks like it falls straight down, which many would look at and say, that's not a parabola. But in fact, when I'm graphing the height with respect to time versus time, let's just say my window is, just for some convenient numbers, let's say this is 16 feet tall. So my initial height of my ball will be at 16 feet. And then gravity starts to pull. And gravity pulls at 32 feet per second each second. So it's making it go faster by 32 feet per second each second. So it goes 32 feet per second, then 64 feet per second, then another 32 feet per second, and on and on. So it's accelerating. It's getting faster and faster. And so the question is, how long would it take to hit the ground? Well, really what we're asking is, what is the time t when h of t is 0? Right? We're asking for the x-intercept. And in fact, we know in a parabola there are two x-intercepts, but physically, this negative time value doesn't make sense, right? You could theorize that if I threw a ball back in time and it went up and landed right at the same time as I was about to drop the ball and didn't have any force, that was its peak, and then it started to fall, you know, there would have been a time where it was on the ground back in time. But that's not the case here. So this part of the parabola really doesn't exist. So what is the time when h of t is 0? Well, let's write our function. The height at any given time is equal to negative 1/2 g t squared plus my initial velocity t plus h initial. So here we're going to have to do some physical interpretation. What are some of these variables? So h of t is equal to gravity, and I notice I have 16 feet, so that makes me think I have negative 1/2 times 32 feet per second squared, because that's the gravity constant in feet, times t squared plus my initial velocity. So the question is, when I let go of that ball, the millisecond, the nanosecond as I let go of it, what velocity is there? Have I pushed it? Have I created any force on it? The answer in this case is no, I haven't. So initial velocity in this case is 0. So I'm going to make a note of that. V0 equals 0 feet per second. My gravity constant, I use 32 feet per second squared. So 0 times t plus my initial height, which we said in this problem was 16 feet, plus 16 feet. So simplifying this equation, h of t is equal to negative 16 t squared, and that's in feet per second squared, plus 16. Now I should know how to solve this problem, especially since I'm trying to, excuse me, let me go back up. Sorry about that, hit the wrong button. There we are. Especially since I'm looking for when height is 0. So 0 equals negative 16 t squared plus 16. I'm going to divide everything by negative 16. So divide by negative 16, divide by negative 16, which those knock out, divide by negative 16. So I get 0 equals t squared minus 1. I add 1 to both sides, and I get 1 equals t squared, which means t is equal to plus and minus 1 second, right? Because these were in feet per second squared. So this will hit the ground. This spot right here is, in fact, 1 second. Now you might say, but after 1 second, it was going 32 feet per second. Yes, but it was going 0 at the beginning, so it took a while to speed up enough to get to 16. So that's 1 second, and the theoretical spot of back here would have been negative 1 second. So if I threw something 1 second before I started keeping time up to this height with some velocity to get there, and then it paused right there at the same time I was dropping it, and it would come down and hit 1 second later. So it would take 1 second to hit the ground.